So the first talk will be BrushLens, hardware interaction proxies for accessible touchscreen interface actuations. Chen, Liang, all yours.
All right, thank you. Hi, everyone. Thank you for coming to my talk. My name is Chen Liang, and I'm a third-year PhD student from the University of Michigan. So today I'll be presenting BrushLens, a hardware interaction proxy for accessible touchscreen interface actuation. So touchscreens are everywhere, but they're not built for everyone. This is because many of them are designed with assumptions about users' abilities to use them. For example, it expects users to have visual abilities, such as perceiving visual interface, locate the button they want to press, and interpret visual feedback. It also assumes users to have motor abilities to actuate these touch screens by performing these predefined gestures in a precise manner. However, these assumptions do not always hold, and it creates a gap of ability assumptions. For visually impaired users, it's challenging to perceive and locate the target button, which significantly reduces touch success rate and hinders independent use. For motor impaired users with tremor, spasm, or low finger dexterity, due to the challenges to perform these predefined gestures, it is more likely to trigger invalid or unintended interactions. And there has been a line of work to make touchscreens more accessible, such as BrushLens and statelens that focus on interface navigation, and recent work such as Touch Ally and Take My Hand for interface actuation. So our work brings an additional perspective to this space. The goal is to bridge the gap of ability assumptions without changing the assumptions made on either side. And specifically, there should be no modification of the touchscreen system for better compatibility, and it should be compatible with existing accessibility tools that users are already familiar with. And also, users should be able to have agency over the interaction. So how could we achieve these goals? So we're inspired by the idea of a proxy, which is an intermediary layer that relays information or actions from one side to the other. We focus on building this hardware interaction proxy, and specifically a phone case with actuators that touch the screen on behalf of the user. So how does it work? The user starts by placing the device on the screen. Given the screen layout, BrushLens shows an accessible interface on the user's smartphone, where the users can use existing mobile accessibility tools to explore what are on the screen and select the button they want to press. And using the smartphone camera and motion sensors, BrushLens can locate itself and the target button on the screen and generate audio guidance on where to move. And inside this phone case, there are some solenoid actuators, which are small actuators with a metal stick in it that can push and pull to simulate a fingertip touch. And combining everything together, users can follow audio guidance and roughly move the case towards the target button. And if any of these actuators is on top of the button, it clicks the button automatically. So with BrushLens acting as a hardware interaction proxy, we can now bridge the gap of ability assumptions. And to achieve this, BrushLens consists of three major components: a hardware case for actuation that determines how to touch, a processing unit for localization that determines where and when to touch, and user smartphone for accessible interface that determines what to touch and where to move. So we know that a successful touch needs to match all these gesture assumptions, such as precisely land and lift at the same spot. And our goal is to let the hardware perform all these touches that match the assumptions we mentioned above, so that the user can delegate the actuation to the device. And we demonstrate two possible actuator setups that can be used in different scenarios. The first image I'm showing here shows the solenoid actuator that can push and pull using electromagnetic force. And the second image I'm showing here is the auto-clicker actuator that electronically alters the screen capacitance to simulate a fingertip touch. And once we know how to touch, the next question will be where to touch. So to solve this, the system needs to know the UI layout and the current device location. And in this work, we assume that the layout is given since prior work has explored automatic layout detection and the interface reverse engineering. And our focus is how to achieve precise localization to determine when and where to touch and generate positional guidance to the target button. And this could be challenging to achieve. For example, what I'm showing here is a camera view from the smartphone when placed on top of the screen. And turns out this is only a very small portion of the whole interface. And in cases where there are visual features, we use an ultra-wide camera to capture the screen and use SURF to detect and match features to the locations on the interface. And when there are no enough visual features, we use an optical sensors to track the movement. And then we add the rotational data from the IMU to collectively estimate the pose. So using this information, BrushLens has a mobile interface for interface exploration and device control. And what I'm demonstrating here is how blind users can use VoiceOver to explore and select the button they want to press.
Wing W0, interface
So the user
buttons,
starts by
heading,
explore
tap to
and
order,
select
button.
the target button.
Target 2-3, now that, 10-3, target 2-3, now that, 9-4.
And then the BrushLens speak out the
7-4.
current position and the target position as coordinates
6-4.
to
Button
guide the
tap to
user
press.
towards the goal. And for motor impaired users with tremor or spasm, BrushLens has a button magnifier mode that enlarges and displays buttons currently around BrushLens to make small or dense buttons easier to select and reduces
Target 8-1, now
mistouches
that,
and the
target
need
8-1,
for fine
8-3,
motor
now that,
control.
button beverage is pressed, target 8-1, now that.
So our technical evaluation shows that both actuators can simulate touches on capacitive screens, and simulated touches are consistent, responsive, and compatible with various consumer-level devices on the market. And our user study shows that for visually impaired users, BrushLens enables them to use touch screens that were impossible to do before independently. And for motor impaired users with tremor or spasm, BrushLens reduces arrow touches by up to 74%. And regarding the user experience, participants gave positive feedback about BrushLens enhancing users' confidence, independence, and the sense of control. As one participant mentioned, I like using BrushLens to push buttons myself. At least I know what's going on. And this is important because I need something that is completely under my hand. And participants also suggest potential improvements, including a more compact form factor and richer audio guidance. So we envision that BrushLens as a platform can support additional interaction needs in the future, such as ability-based needs, for example, a flexible band for grasp support, scenario-based needs, such as smaller form factor for smaller touch screens, and gesture needs to support other multi-touch gestures. And with that, I will conclude my presentation, and thank you for listening. I'm happy to take any questions.
Okay, thank you for the great talk. This is a very cool system. I know some touch screens are displayed vertically, not flat. Do you think your design will need changes for those vertically set up touch screens?
So the system works on vertical screens, but the challenge is that the current form factor is pretty heavy. So we basically have two different cases. We have a solenoid case and the auto clicker case. And the auto clicker case is pretty light, but the solenoid case is like 12 grams per solenoid. So for the auto clicker case, because everything is electronic and everything can be integrated into PCB, we envision that could be built as a phone case, so that as long as user can hold the cell phone, it should be able to work on the vertical screens as well.
Thank you.
Yihao Carnegie Mellon. So a wonderful talk. I really like the point where you can breach the accessibility assumptions for both dexterity and vision access in a single pseudo system. So my question would be, could you comment about the onboarding process for like either blind or people with motor impairments, where you said that there's an assumption that UI layout is like kind of already known by the system, but I also wonder, could you comment a little bit about would you expect that the users will use your device to kind of scan through the whole touchscreen, or like you'll use like something like BrushLens or StateLens that you need to hold the device and kind of scan through the whole screen to kind of reverse engineer or reconstruct the UI layout?
Okay, so that's a good question. So basically, there are two parts before our work. So one is to capture the image of the interface, and another one is to determine the layout of the interface. So like you said, to capture the image, there could be audio guidance for the users to take a picture of the interface, or scanning or brushing on the interface to staging the image. And once we have this image, we can use like prior work to automatically determine the layout. So yes, that would be possible.
Okay, thank you.